Namaskaram. In this session, we will see normalized vector and inner product induced by Euclidean inner product. Okay, first we consider unit vector. A unit vector is a vector having a norm of 1. Okay, for example, we consider x is equal to the vector 1 by 2, 1 by root 2, minus 1 by 2 belongs to R cube. Then how to find the norm x? Norm x is defined by inner product of xx. Okay, here I am going to consider Euclidean inner product. Nothing specified, then always we consider the standard inner products on Rn. That's our Euclidean inner product. Okay, and this is equal to, okay, by definition, this inner product is equal to 1 by 2 square plus 1 by root 2 square plus minus 1 by 2 square. And this is 1 by 4. This is 1 by 2, 1 by 4 plus 1 by 2. Again, this is 1 by 4. So, square root of 1, right? That's equal to 1 because we consider the positive square root. So, here norm of x is equal to 1. So, we can say that this is a unit vector. You got it? So, if norm is 1, then we can say that the vector is unique. And that depends, and this value depends the norm. Okay. That means if you use another norm on the same vector, maybe that norm is not equal to 1. Okay, so unit vector is defined, or the concept of unit vector is with respect to the norm. Okay, for a particular norm, if norm x equal to 1, then we can see that that vector is unit. Next definition, if x is a non-zero vector, then normalized vector is defined by 1 by norm x into x. Okay, we know that norm x is a scalar, it's a number, real number. So 1 by real number, it's again a real number. That real number into a scalar into vector. Okay, and the important thing is x should be non-zero. This means, suppose we consider an inner product space C, and we consider an arbitrary vector x from this space. If x is non-zero, only assumption is x is not a zero vector in that vector space. Okay, if x is non-zero, then you can find a new vector like this, 1 by norm x into x. That's another vector in V. Okay, so and this vector is called the normalized vector corresponding to x. Here, suppose norm x equal to 1. Suppose x is a unit vector. Then what about the normalized vector? The normalized vector is same as x because 1 by norm x is 1. So if x is a unit vector, then normalized vector is same as the vector x itself. Okay, next property, normalized vector is a unit vector. Okay, for example, you consider a vector x which is non-zero, and next we are going to find the normalized vector. How to find the normalized vector? We just consider 1 by norm x into x. This gives a normalized vector. So corresponding to this non-zero vector, we can define a normalized vector. And we have to show that this new vector is a unit vector. Okay, so how to let it be u. Suppose we consider the normalized vector as u. Then how to prove this is a unit vector? To prove it is a unit vector, you simply show that norm u equal to 1. If norm u equal to 1, then you can say that u is a unit vector. Okay, so you simply consider norm u. And by definition, this is equal to norm of 1 by norm x into x. Okay, and we have a property for norm x, that is norm of lambda x. What is norm of lambda x? That is mod lambda into norm x. It's a property of norm. So here what happens? This is equal to modulus of 1 by norm x into norm x, right? And what about modulus of 1 by norm x? Yeah, that is 1 by norm x itself. Why? We know that norm x is always greater than 0. So its modulus value, this is positive. Norm x is always positive, not negative. So its modulus is same as itself. So that's why 1 by norm x into norm x, right? This is norm x. And that is norm x by norm x, that is equal to 1. So norm of u equal to 1. That means u is a unit vector. What is u? U is our normalized vector, x by norm x. So normalized vector is always a unit vector. Its norm is 1. Okay. Next problem. Find the normalized vector of x is equal to the vector 1, 2, 4, an element of R3. Okay. So how to find the normalized vector? The normalized vector is defined by 1 by norm x into x. So first we have to find norm x. And how to find norm x? It's equal to positive square root of inner product of xx. And x is here. Then how to find inner product of xx? We consider the Euclidean inner product. Okay, we know that is x transpose x or whatever way. Anyway, its inner product become 1 square plus 2 square plus 4 square. And this is equal to square root of 21. Right. So the normalized vector is equal to 1 by root 21 into x. What is x? X equal to 1, 2, 4. Right. So 1 by root 21, 2 by root 21 and 4 by root 21. This is the normalized vector corresponding to this vector. It is clear that its norm is 1 because we know that all the normalized vectors are unit. You can verify. Okay, next problem. If u and v are orthogonal vectors, then norm of u minus v square is equal to norm u square plus norm v square. So it is given that u and v are orthogonal. That means inner product of uv is equal to 0. And also we know that inner product of uv and inner product of vu are same. So this also 0. Okay. So we consider left hand side. This is norm of u minus v square. What is norm of u minus v square? By definition, okay, norm u is that. What is the definition of norm? Yeah, inner product of norm x is equal to square root of inner norm x is equal to square root of inner product of xx. So this square is there. So this become inner product of u minus v, u minus v. Then you can expand this inner product using the distributive property. So what happened? So this become u comma u minus v plus inner product of minus v u minus v. Right. Again, you can expand this using another distributive property. So this become uu plus u minus v plus, and this is nothing our norm u square, and by the property of inner product of some u comma lambda v, that's equal to lambda into uv. Okay, you can take minus outside, so this become minus 1 into uv. Similarly, this become minus 1 into vu plus, and we have two minus signs, that means minus 1 square into vv. So this become norm u square, and what about the inner product of uv? That is equal to 0. Okay, so this term is 0 and this term also 0, and this is norm v square. So if u and v are orthogonal, then norm of u minus v square is equal to norm u square plus norm v square. Okay, next we are going to define another class of inner product. That inner product is induced or defined by Euclidean inner product. Okay, let's see. Let V be an n-dimensional vector space and x comma y belongs to V. Then we consider two elements x and y. Then we define an inner product on this vector space. It is the Euclidean inner product on the coordinate representations of both the vectors with respect to the same basis. That means we consider a basis for V. Okay, we consider a basis B for this V. Let B become B1, B2, etc. Bn. We consider n vectors. Okay, we assume that B is an n-dimensional vector space. So this basis contains n vectors. Let it be B1, B2, etc. Bn. Okay. Then this inner product is defined by Euclidean inner product on the coordinate representations. So how to find the coordinate? First we have to find the coordinate of x with respect to b and coordinate of y with respect to v. And how to find the coordinate of x with respect to b? First we have to write x is a linear combination of basis elements, right? Etc. plus some cn bn. Then what is coordinate? Then coordinate is defined by the scalars in a column vector, that is c1, c2, etc. cn, right? Similarly, you can find the coordinate of y with respect to b. Let it be some d1, d2, etc. dn. Now, what happened? These coordinates are our elements of the form Rn, because they are column vectors with containing n entries. So we can treat they are an element of Rn. So now you can define. We know that how to define the Euclidean inner product on Rn. So you can take the inner product between these coordinates. That's a definition of inner product between x and y. Okay, so this is defined by the Euclidean inner product between these coordinates, coordinate of x with respect to b and coordinate of y with respect to b. Right, we know how to take the Euclidean inner product. How to take the Euclidean inner product? That is equal to c1 d1 plus c2 d2 etc. plus cn dn. So whatever be the vector space, if it is a finite dimensional, then you can choose. Then you choose a basis, particular basis. Then you can find two column vectors corresponding to any given two vectors. Then you consider the Euclidean inner product between the column vectors. That is the definition of this new inner product. And this inner product is called inner product induced by Euclidean inner product. Okay. Okay, naturally this induced inner product depends basis. If you choose another basis b1 for this v, then of course these coordinates are different. X with respect to b1 is different. Okay, similarly this also different. Coordinate of y with respect to b1 is different. So automatically this inner product is different. Okay, so induced inner product depends basis. Okay, evaluate inner product xy for these two matrices with respect to the standard basis. Okay, we have to find this induced inner product. Okay, then how to find the induced inner product? First, we have to find the coordinate of x with respect to the standard basis b and coordinate of y with respect to the standard basis b. And what about b? What is standard basis for this collection? And we know that these matrices are from the collection m2 by 2, right? So what is the standard basis for m2 by 2? Yeah, it contains four elements 1 0 0 0. Yes, this is the standard basis for m2 by 2. So what is the coordinate? So what is coordinate of x with respect to b? This is very easy. Then you can easily write this matrix as a linear combination, this one. Then what is c1 c2 c3 c4? Yes, that is 4 3 6 2. Okay, and similarly what is the coordinate of y with respect to b? Yes, that is 1 2 1 2. Now these are the coordinates of these two vectors with respect to the standard basis. Then now you are ready to define our induced inner product between them. The induced inner product is defined by the Euclidean inner product on the coordinate representation. And these are the coordinate representation. Then what is the Euclidean inner product? 4 into 1 plus 3 into 6 plus 6 into 1 plus 2 into 2. Okay. This is same as our x transpose y. Okay. Actually here not x transpose, instead of x, this is x with respect to b transpose y with respect to b. Okay, anyway, this is the, and what is the final answer? Oh sorry, this is 3 into 2. Okay, so 4 plus 6 plus 6 plus 4, that's equal to 20. So the inner product between these two matrices is 20. Yes. Next one, calculate the inner product between p of t and q of t with respect to the standard basis in p square for p of t equal to 3t square minus t plus 5 and q of t equal to minus 2t square plus 4t plus 2. Okay, so first we have to find the coordinates of p of t and q of t, then take the Euclidean inner product. Okay, what is the standard basis for p square? Yes, t square t1. This is the standard basis for p square. Then what is the coordinate of p of t with respect to b? First you write this p of t in terms of base elements, then you write the coefficients. So it is clear that it is 3 minus 1 5. And similarly, what is the coordinate of p of t with respect to b? that is equal to minus 2 4 2. Okay, so now you are ready to take the inner product between P of t and Q of t. That's equal to, this is minus 6, and okay, so this is 3 into minus 2 minus 1 into 4 5 into 2 minus 6 minus 4 plus 10, that is equal to 0. So here the inner product equal to 0 with respect to this induced inner product with respect to the standard basis. Okay, so with respect to this inner product we can say that these two vectors are orthogonal. Okay, because their inner product equal to 0. Okay, anyway, the induced inner product depends the basis. So this is your homework. Actually, the second problem, the question is same. The x and y are same as our first problem in our classwork, but the basis is different. Okay, so you have to find the induced inner product with respect to this basis. Okay, thank you.